Hello everyone. Next, I will show you some results about the constructions of ZK snarks. Now let's start. What's zero knowledge proofs? Basically, you have two parties. One is the prover, another is the verifier. The prover wants to convince the verifier some statements through some numbers or round of interactions. At the end of the interactions, the verifier just decides to accept or reject. And also the prover doesn't want to reveal its secret information. Here is an example. The prover S and the verifier both engage some zero-knowledge proof protocol to prove the statement X through some number round of interactions. Certainly, we are interested in those protocols that have some special properties. First is completeness. It means the prover and the verifier both are honest, then the prover can convince the verifier if X indeed is true. Second is soundness. If the prover is malicious, then she cannot convince the verifier if X is not true with a high probability. Third is zero knowledge. If the verifier is malicious, then he cannot learn anything more than the validity of X. Here is some applications of ZKP. For example, we can use the range proof to prove some number in a given range without revealing the exact value of the number. Other applications include the membership proof, bid auctions, and voting, and so on. Now let's look at what's R1CS relation. Basically, an instant X is a tuple which includes 7 elements. Here, matrix ABC is 3m times m matrix. V is the public input vector. W is the private input vector. And we also assume each matrix has at most n non-zero entries. Now the R1CS relation is to ask whether there exists a witness such this equation holds. Now, given our sense instance over the field F, we choose firstly a fan space H with size M. Then the matrix A actually induces a mapping in some canonical order. Mean any entry in the matrix A can be accessed with 2 entry identifier. Similarly, any element of Z can be accessed with an entry in H. Now we define a function fwx equal to this. Fwx is used to encode the vector Z, which includes the private witness W. Then the R1CS relation can be converted to this satisfaction problem. This means every X in the set H is 0 of the function fw. If we use polynomial interpolation, here the function fw actually is also polynomial. This means every X in the set H is a root of the polynomial fw. Then we use some algebraic technique to convert this polynomial satisfaction problem to this. Using the foundation theory of algebraic, this is equivalent to that there exists some polynomial g, which degree less normal than m minus 2, such that fwx equal to zhx times gx. Then this equation can be verified at random points, which is chosen by the verifier. Of course, this is associated with some soundness, by the short-slipper lemma. We can also reduce them furthermore as this. Let fw equal to this. Because the fw, by the definition, fw is equal to a times b minus c. Then we compute arx, brx, crx Then the prover made three separate claims this and send this three new values to the verifier. Then the verifier evaluates the GRX and ZRX locally, which in turn enable the verifier way to verify this equation. But here the prover made three new separate claims. So the verifier we must still verify this new claim from the prover. That we can do this in a very efficient way, not to do them separate one by one. Idea is the verifier sum three challenges and send them to the prover. Then the prover prove this combined claim. We can further write this combined claim to this. Actually, this combined claim is a sum check. Then we using the univariate sum check protocol. Remember that in the univariate sum check protocol, in each round, the degree is reduced by half. Then, however, we need some initial conditions to step forward the univariate sum check. Here, the initial condition is some evaluation of the polynomial Qx at some random point chosen by the verifier. Write them out explicitly here. The only term in Qx Ry depends the prover witness is ZRy. Here Rx, Ry, and Ra, Rb, and C is all chosen by the verifier. The prover can commit the vector Z at the beginning of the protocol and open to the points the verifier queried with their Merkle tree proof. We're using the Merkle tree commitment to commit the vector Z. All the other items in the above expression determined by the instance X and can be computed locally by V. However, this takes at least linear time, it's still linear time. We cannot, because in practical, the verifier usually has very limited computing power, cannot afford the linear time complexity. How to efficiently compute MRXY for each matrix. This is our main contribution in this paper. We define this bivariate polynomial delta hxy equal to zhx minus zhy divides x minus y. The individual degree is the size of h minus 1 because if x equal to y, certainly zhx equal to zhy. So the x minus y is a factor of the number weights. Now we choose the h as a offense weight, so the polynomial zhx has a very special form, so-called the linear rest polynomial. Now we write the expression of delta x is y. If in the case x not equal to y, the delta x y can be read as this form. If x equal to y, we cannot do it like that because x equal to y, x equal to y 0. We cannot divide by 0. But we can consider this as a discrete derivative. Then evaluate x. Actually, this is equal to C1. It's a non-zero constant. Then let's row, column, and value represents the row index, column index, and value of the non-zero entries of matrix M in some canonical order. Recall that the computation MRXY, the zero interest don't make any contribution to the computation. So we need some method to filter out the non-zero interest. We're using the delta H function delta H defined previously. Then this MRX equal to this. The first term can be computed by the verifier very efficiently. And the second term only contains the non-zero interest or has only linear term, linear. Then we use GKR to compute this query because the GKR protocol is doubly efficient protocol. And also our computation is very, has many repeated substructure. So we can use the GKR protocol to compute this in a very efficient way. Here the proof time is linear and verifier is log n square. The table below is the overall complexity and the comparison with some other schemes. We also have some concrete benchmarks. Here is the proof running time. Here is the argument size and verified running time. Our scheme is not one that win in every perspective, but it can provide the trade-off in some practical applications. Well, that's all we've done in our works. Okay, thank you for your attention. Now, any questions?